Hello, everyone. Hope you're doing all right. Today, we're starting chapter 4 and another phenomenal chapter. And we're going to start with this lesson here. So, we're talking about how do you calculate the exact area in this lesson. Now, before we get into this, let's recall that in chapter 3, the question was how do you calculate the exact slope or rate of change at a moment. Let's say that at a moment. How do you calculate the exact rate of change at a moment, all right, rather than over a given interval? And the way we did that is we talked about the derivative. And the definition of that was we did the derivative was equal to, now we put 2 points between them, which we used f of x plus h minus f of x over h, and we looked at the slope between those points. And the way we got the slope at an exact moment was not only using our understanding of the slope, but it also used the idea of limits and that we wanted h to approach 0. And this is very similar to how we calculate the exact area. Okay, so let's say we have a function, arbitrary function f of x. And we want to find the area from A to B. Right? If we wanted to find the area under the curve from A to B of an arbitrary f of x, now we would, in the past, what we know how to do is use Riemann sums. And if we wanted to use, say, left endpoint here, let's say we had to use left endpoint for n amount of rectangles, what would it be here? Well, it's going to be the area under the curve is from x equals 0 to n minus 1. Remember, there's always one less than the number of rectangles. And then the width of each rectangle, which is going to be b minus a over n. And then we would evaluate the height of every rectangle by looking at the first interval, which is at a, so f of a plus, and then that rate of change is changing for each summation there. So that was the general form to get the area under the curve left endpoint for n amount of rectangles. But how do we get the exact area, right? Well, notice if I just did a few rectangles, if I did, how many is this? 1, 2, 3, 4 rectangles, it's not that good of an approximation. What if I did more rectangles? If I ended up using, say, 8 rectangles, but then my first one would look like this, second one, the next one, the next one. And when I use more rectangles, there's less error. And I could keep going. And the idea is, how do you get the exact area? Where the idea is, the more rectangles, the better. The more rectangles, the better approximation of the area. How many rectangles is going to give the perfect amount? Well, it'd be nice if we could have an infinite amount of rectangles, but there's no such number as infinite. But how can we approach infinity? Well, we can use this area still and just add on the limit as n approaches infinity. And that right there is the exact area under a curve. And notice it's just like the slope before, where you needed 2 parts. You needed the slope between 2 points and the limit. And just like exact area under curve, you need a Riemann sum, which we knew how to do, and the limit. All right, 2 things are needed. Now notice with derivative, this equals the notation f prime of x. What this equals is called an integral from a to b, because that's the interval we're looking at, of f of x dx. And that I'm going to highlight because that's the notation we use to represent exact area. All right. So again, if I was saying this in words, that's the integral. That's what that notation is, from a to b of f of x dx. Now let's understand what this is, and I'm sure you can read the math notes and figure it out. But a to b is defining the range, the interval we're looking at. F of x is the curve we're looking at. What area under the curve do we want? And the dx is equivalent to the width of every rectangle. So that's like the b minus a over the n, where the f of x is like the height of every rectangle. So notice you need both parts, right? You can't just write a to b of f of x, because then you're just saying, I have the heights, let me find the area. That's not true. You need the height and width. Now, one thing to note is that as n approaches infinity, what's happening to the width if you have a constant over infinity? Well, small over big, it approaches 0, which makes sense. The more rectangles you have, those rectangles are going to get smaller. So there it is. That's called an integral. That's how you get the exact area under the curve. So when we write this, just like how I write f prime of x, just know what it means. Right? This is equivalent to this. So let's do an example, and I'm going to wrap this up to try to keep the video shorter. All right, let's find the integral of -2 to 3 of x plus 4 dx. Okay, so I want to find the area under the curve of x plus 4, and then there'll be width dx that changes in x, which will approach 0. But they won't be 0 because we're taking infinitely many of them. So if I was to sketch this curve to help you see it graphically, x plus 4 starts at, I didn't draw this too well, sorry. Fix this really quick. Down here, x plus 4 starts at 4, 1, 2, 3, 4, has a slope of 1, like so, and we want to evaluate from -2 to 3. Right. So what this notation is saying is what's the exact area under this curve right here. Right. So what's the exact area under x plus 4 from -2 to 3. Okay. So if I was to write this out, I'm going to push this up a little bit, write it out using its definition, -2 to 3 of x plus 4 dx. Well, that's equivalent to the limit as n approaches infinity of its general Riemann form, so x equals 0 to n minus 1, of the width here, which is going to be 3 minus -2, which is 5. So it's 5 over n, over f of -2 plus 5 over n x. And I guess I could have just written 3 minus -2, but that's fine. Okay. Now, you could actually put this in a calculator. So if using a calculator, I'll show you that in a second. But I know in your work today, it says no calculator. So how do we do this no calculator? With this problem, we can do without a calculator because we have a shape that we know, which is a trapezoid. So then we could find the area, the exact area of here by doing 1/2 times f of -2 times f of 3 times the height of 5, which would give us -2 plus 4 is 2, 3 plus 4 is 7 times 5. That gives us 9 times 5 is 45. So we get 45 over 2, you know, whatever unit it is. Well, it's actually not unit squared. Be careful when we talk about area under the curve. They can represent different things like an amount of something. Like the area under the curve of a velocity graph is the amount of miles traveled. So we'll just say 45 over 2 for now. We don't know what the units are.